Thanks to the organizers for inviting me to come to this workshop, not only for this opportunity to talk a little about some things that we've been doing lately, but also to learn from all the specialists that have been making this a really nice workshop. So first of all, let me just say, I'm from a brand new university here in Brazil, the Federal University of ABC, which does not mean that we're alphabetizing university students, right? Rather, this is an acronym for 3 satellite cities of São Paulo capital, and we're building a university from scratch over there. We've been doing so for the past decade or so. And I'm over there, we founded this quantum materials group, which despite the name actually works or operates in a very broad spectrum of condensed matter physics, and maybe in this talk you will get some idea of the things that we've been involved in. So what I want to show you, this talk, it's a new talk that I've started giving this year, and because of some papers that came out recently, and what it looks like is more like a show and tell, right, of things that I've been doing over the past 15 years or so. And this is pretty much how it happened historically. So first I'm going to talk about the ytterbium compound in the series together with its cousin, the germanide. Then I will go into more, so these are strongly correlated systems. Then we're going into some less correlated electron systems, completing the series with the magnetic compounds, and finally looking at the non-magnetic ones, looking into the superconductivity that has developed in those. And I very much doubt that I'm going to have any time to talk about that, but let's see how it goes. Well, so going back 15 years ago, I was a postdoc in Hiroshima, and our group, and me specifically, we're in the business of hunting for materials that are either completely unknown or almost completely unknown. If every once in a while one of these compounds is useful for academia, we're happy, right? And if every once in a very while one of these compounds is useful for society in general, then we are very happy, right? But in general, the fun is in actually finding out these new compounds. So at the time, I decided to check this compound, inspired by some of the cerium equivalents in the 113 structures of materials. And voila, right, on the very first attempt, just by mixing these elements in tin flux and doing some standard broad range slow cooling, we immediately got some beautiful crystals there, which were basically limited by the size of the ampule itself. So it seemed that it was just a happy system to grow. No further optimization was necessary at the time. Give a child a new toy and he starts playing with it, right? So then we started characterizing it. With the resistivity, we could already identify that this showed Kondo lattice behavior, right, with that typical long T increase coming down here at low temperatures. And down here, we could see that way below the temperature, it was actually a little surprising that we had a rather high Néel temperature for an ytterbium compound, so it's above 5 Kelvin here. And well below that, we could see Fermi liquid behavior with small a value like that. Highly metallic compound, right, with triple R over 40 in this case. Going into the magnetization, looks a lot like we've just seen right now, so it's an isotropic. This is an orthorhombic but quasi-tetragonal system. And in this case, the spins seem to align along the b-axis from the susceptibility here. And when we do the magnetization at low temperature, we do see a spin flop over here at about 1.7 Tesla. And then moving up, we can see the end here of the ordered phase at around 8 Tesla, which is actually not so high, reasonably within the range of common systems there to measure. Notice that the saturation moment here is quite low still, right, around 2 Bohr magnetons here, which does suggest that we have a hybridizing system. This becomes clear when we do the specific heat. So we've got this beautiful lambda peak here, a very sharp one. This gives us a gamma of around 200 millijoule per mole Kelvin square, which suggests a Kondo temperature that should be around 30 Kelvin. And by integrating the entropy up here to the transition, this is something that's close to what we've recently seen, right, with the rhodium-2 silicon. So it's around 0.6 Rn2. And the A over gamma square here maps almost perfectly onto the Katawaki-Woods ratio. So it seems like we have a nice model system here, right, of a hybridizing system with a Kondo lattice, and with the difference of actually having a pretty high Néel temperature for ytterbium compounds. Continuing to play with that, then we started applying pressure just to see where it goes. From here, we can see that both by applying pressure and by applying field, basically what we do is destroy the Kondo lattice scattering here, and with the pressure, we can see that the temperature, the Néel temperature, just goes down almost monotonically, which then suggests that within the Doniak scenario, we are right up there near the top, right? And as we apply pressure, ytterbium moves in the opposite direction of cerium, right? So it starts moving away from any possible quantum criticality here. But with the magnetization, we see that we get the same effect, right? We start destroying the Kondo state up here. But this gives then the possibility of finding a field-induced quantum critical point, similar to what was shown here with the rhodium-2 silicon-2. So our next step was then to map that in collaboration with the Ames group. And unfortunately, although we did quite a thorough mapping of here, following how resistivity went and built the phase diagram here, as you can see here, right from the Fermi liquid equation here, look at the A and the exponents here. They don't really deviate much in this case. So it just seems that through this route, right, of applying the field, at least the way we measured it this way, it just seems that there's no field-induced critical point there. And the next thing that we can do then, if we're still looking for a critical point, then we have to think about expanding the lattice in the system, right? And so the standard ways of doing that would be to substitute the elements with larger ones and see if we can get that. Unfortunately, nature wasn't very favorable in this case, so when we try to replace nickel with palladium, we just don't get any inclusions of palladium in there. There's basically no change in in Tn of the ytterbium in these the crystals that came out of here. And when we try to replace silicon with germanium, we actually get back to the original one with basically no germanium in, and this new compound that we found out. So this opened up another branch, right, of the 216 family, which we later just published as a series of ytterbium mixed valent compounds here. So this just gives you an idea how sometimes even our failures are fun to explore, because you end up opening branches like that. But no, this is a whole new topic of the 216. Going back to the 113, what we were able to do was, with the pure compound, we got the 113 germanite. And this one then showed to be more promising in this case, right? So because we were then able to apply pressures and follow the resistivity, then you can see the magnetic scattering going up as we start applying pressure, right, like this. And then when we do the Fermi liquid analysis, in this case, we can see that the beta exponent is going down from just basic electron phonon scattering down to what can be close to a Fermi liquid, and then further down, pointing towards 1.5, which would be the spin fluctuation theory. And you see the A parameter going up almost in order of magnitude. So this gives us an indication that somewhere around 8 Tesla here we have a quantum critical point. So the scenario that we have in this system then, just summarizing, would be ytterbium nickel silicon 3 with a valency very close to 3 somewhere up here, and ytterbium nickel germanium 3 somewhere mixed valent in this region, through which, when applying pressure, we can move it to this point. Unfortunately, for the resistivity, we didn't have enough pressure to go there, so we started looking for collaborators, and we got the interest of Professor Hitoshi Sato, who is a specialist in synchrotron scattering experiments over at Springate. And so we proceeded to analyze and do that. And so again, I thank Cornelius for giving a nice introduction for that, so I can skip most of the description of what these experiments involve. Basically, the idea is then you can look at signatures, right, spectral rates referring to divalent and trivalent ytterbiums. So from the absorption spectra, we can see that indeed the germanide is right around 2.5, while the silicide is close to 3. But in order to get a better resolution of that, they went on to do a little more sophisticated variations of this involving partial fluorescence yield absorption and resonant X-ray emission spectra. The nice thing about it is then you can get those 2D maps like was shown in the previous talk. You can then find out not only the absorption, right, but the energy transfer, and then use that in order to map the spectral weights of the different valencies. And the nice thing that we could see from this work is how different techniques or different variations give us better resolutions, depending on which compound we are measuring. So it was clear from here that when you do the absorption spectra, you get very nice resolution for the germanide, which is around 2.5, whereas in the emission spectra, we don't get almost any signature from the trivalent one, right? So this is rather low here. On the other hand, when we look at the silicide, we don't see almost any signature of the ytterbium 2+ here. On the other hand, in the emission spectra, we do get a nice signature up here. So this allows us then, by looking at the two different techniques for the two different compounds, we get much better resolution of the effective valencies, and then we can start doing things like mapping the temperature dependence, right, which gives us, showed us in general that there wasn't much of a change in these cases. Then from there we went on to the pressure dependencies, and then as we expect, right, in the case of the germanide, you start killing the divalent one, raising the trivalent one, and then by plotting all of these results together, we could see that basically for the silicide, it just basically remained up there, didn't change much above 2.9, whereas in the germanide, you could clearly see it moving from around 2.5 up to around 2.8, 2.7, and maybe some regime crossover here as it crosses the region where the quantum critical point should be located there. So one of the conclusions we can get from this part of the work was then, for this case, we can see that the ytterbium valence is still highly hybridized and fluctuating as it crosses the point, right? So if we think about the general scenario of quantum critical points whose theories have been put out by several people, right, who are here in the audience right now. So what we expect then is that for this system, we have one of those where we cross the quantum critical point with the F electrons still pretty hybridized, so they pick up the Q vector, right, and there's a reconstruction over here, broken symmetry and so on, but it's not one of those cases, for example, where the Fermi surface collapses and the 4F electrons just move away from the Fermi surface. So, okay, that's pretty much how far we got with this system, the ytterbium systems. And well, at the time, I promised that I would look at the rest of the system because basically nothing was known about them. And I only had this opportunity to do it in the more recent years here in Brazil, together with my master's students, Daisy, and the postdoc, Fabiana. And this came out a few months ago, this publication here, which is sets a couple of benchmarks for us, which I'm a little proud of. And so I'd just like to point out the following, that in this work, we have, in the co-authorship, we have 6 women and 3 men. So at least that's one nice, something that's, you know, it's pretty matter of pride for me. I don't know if that's a record. If you know anything, any work that is something like that, please let me know so I can brag even more about it. Another benchmark here is that this is the largest publication we've ever had. It's 21 pages in PR format, and it's our first paper in the PR materials, which at least I think is a welcome addition to the material spectrum of publications. So here's and I want to give proper credit where credit is due, is that later on, when I was working with the ytterbium compounds, in the beginning, nothing had showed up on them. But then later on, I guess this paper got indexed and started appearing. And it's a Ukrainian paper from 1977, published in the Ukrainian Journal of Physics in Russian. And what they did was arc melt all of these samples and publish the high temperature paramagnetic susceptibility, right? So I just want to give proper credit, right? The person who discovered this was Gorilenko et al., right? So what we did was pick up on that and growing with some twisting of the technique that we use for ytterbium, we were able to grow all of the crystals. And then we started characterizing these ones along the series. So first of all, looking at the X-ray diffraction, everybody maintaining the same space group and same structure in general. What we do note around the series is that while they start out as slightly orthorhombic with around 1% distortion in the AC plane, as they move along the series, it just becomes almost totally tetragonal, right? So 0.1% distortion up there. And as they move along like that, the B direction where this layered structure stacks up, it starts getting more elongated. So the next few slides that I'm going to show you is just going to be a massive amount of data, a lot of information to absorb quickly. So what I'm going to do is I put on some arrows here to help me and you look at some of the things that might be worth looking at. So the first case, and the series only grew starting at gadolinium. It didn't work out yet for the lighter rare earths. So for gadolinium, first thing we can see, right, as expected, you can see that the entropy just goes up right into the R log 8, showing the octuplet participating here. So it might seem that it's just a very standard gadolinium system, but actually it's not that much. When we look at the ordered state, now we can see that the spins in this case are aligning along the A direction, right, going nicely down to 0 here as it orders. And indeed, in the A direction, we see a spin flop. But while for most gadolinium compounds, the spin flop already goes right up to the saturation magnetization of gadolinium, over here, that doesn't happen at all. We are after the spin flop, we only get 1 Bohr magneton per formula unit, and even up to our highest field here, we were only at 2 Bohr magnetons here. So there's something different happening, especially as we see that by increasing the field in the spin flop of an anti-ferromagnet, the spin flop temperature field is increasing rather than decreasing. So there's maybe some extra things here that need to be looked into. As we move on to the terbium compound, again, I call your attention to where the spins seem to be aligning, right? In this case, again, in the A direction, but it starts picking up a little bit of signals in the other directions. You're going to see how this trend goes along the series. In this case, you can see that indeed, after the spin flop, which has some intermediate steps, it goes right up to the saturation value in the case of terbium. What's interesting in the case of terbium is that we start seeing several metamagnetic steps, right, intermediate steps here. And these steps seem to show an alternation of irreversible and reversible regions. So this is an indication that we might have these typical cases where you have to take into account not only the nearest neighbors, but next nearest neighbors and maybe a few others. So then we start getting these intermediate arrangements, right, which may ultimately lead to a devil's staircase type scenario. Another possibility that can explain this, we still haven't figured out these things yet. Everything here is very new. But we have already noticed that in this system, for some of the materials, they can be nickel deficient. So maybe some nickel deficiencies could also contribute to producing some intermediate steps, especially these initial ones, very low ones here, could be somehow related to that. Moving on to the dysprosium. Again, we are still with the spins aligned along the A-axis, but now you can see that the other axis, the c-axis within a plane, is already picking up some susceptibility in this case. Again, we can see the spin-flop transitions with intermediate steps, with alternations of hysteresis and non-hysteresis in the middle of the intermediate steps, and going up right up to the saturation value above 10 there. Still moving then up, going to the holmium compound. Now we can see that holmium actually presents itself as a very different system. It shows two transitions in the specific heat, and more interesting than that, we can clearly see that the two transitions actually have different temperatures. So this was pretty surprising for us. We had never seen any example of that. It just seems that the behavior in the two in-plane measurements are quite different. Fabiana did find this conference paper from a few years ago showing a precedent for that. So in the rhodium-2 silicon-2, there is indeed this case where in the two different directions you can see two very different temperatures here. And what they have proposed in this case is that they're getting component-separated magnetic ordering, right? So which means that at one temperature you just get one component of the spins ordered while the other one is still loose, right? And then only further down do you order the component, the second component. Another possibility here could just be that the magnetic structures in the two orientations are different, which may lead to different nail temperatures. So this is another thing that's ongoing. So I need to accelerate if I want to talk about superconductors. So moving on to erbium, now I just want to show that we have now flipped from the A-axis over to the B-axis, but there's also the other C-axis here also participating in the saturation. Again, we have metamagnetic transitions, which now are more rounded because the actual temperature, the nail temperature, is coming down, getting pretty low. And finally, in the thulium, we have completely changed over to B-axis alignment, right, with almost no signal of susceptibility in the plane. And as you remember, in ytterbium, we had them perfectly aligned in the B-axis with no signal of the in-plane. So with that, we can just do our standard analysis along the series and find out how they behave in general, thinking about crystal electric field and the de Gennes scaling and so on. It does call attention, as I mentioned before, that gadolinium does not behave well in this system, and you can clearly see that here, right? When you do the de Gennes scaling analysis, you can see this going up almost linearly as you would expect, but then gadolinium is not there where it should be. For some reason, the nail temperature of gadolinium is much lower, comparable to dysprosium and terbium. So something to explore that. And so what we have here, published, right, and available to anybody interested, is the basic characterization of all of these magnetic compounds in the series with lots of data here for further exploration. So in the very few minutes I have left, I just want to quickly then show the non-magnetic ones, which were initially used as non-magnetic references, right, for all of this analysis. And that's because at the time we were doing this work, we did not have access to below 2 Kelvin temperature. But then my postdoc went back to Hiroshima together with Professor Takabatake there and took these samples to measure lower there, and then we immediately found then superconductivity in both of them. One of them is at 1.40, where did I get? Okay, let me change here. This is the better one. So one of them is at 1.36 in the case of yttrium, and the other 1.61. So nothing really strange about this, right? Okay, so they're non-magnetic. You went to low temperatures, you found it. What is interesting about this, and I won't have time to explore a lot of that, first of all, look at, we have 100% bulk superconductivity here, right? So this is the full volume superconducting phase. But what is interesting here is that these are two cases of type 1 superconductors found in a ternary system, which notably has defects. It has nickel vacancies. So historically, everybody says that type 1 superconductivity is for the elements, right? Then a handful of binaries came out and then said, okay, binaries are also in the game, right? Then later, ternaries came out, and say, okay, maybe less than a handful of ternaries, but they have to be very clean and perfect, right? And now we have a case of type 1 superconductivity on a system which, for example, for the lutetium, we know that this one actually has as much as 30% vacancies in the nickel site. This might actually mean that this system is moving between the 113 phase and that 216 phase that I had shown earlier, because the basic difference between those two is one layer of nickel. So this is something that, again, we're working on exploring in this case. Well, my time is so again, right, we have, this was just submitted last month. Maybe the referee is in the audience, right? And so we have all of the data, the basic data on these two new superconductors for further exploration there. We also have the data on the electronic structure. You can see it's a highly anisotropic Fermi surface, right, with multi-band surface here. There are two highly two-dimensional bands in this case, and one three-dimensional one, two hole characters, one electron character. So I won't have time to show some of the preliminary works. Let me just go back here and just summarize the talk then, just with the messages about, what have we learned with the new system. So the ytterbium ones is a quantum critical system, as I showed you. The nickel silicides, we found antiferromagnets, highly anisotropic, and with lots of metamagnetic steps. In one case, a double transition, and lots of magnetic phenomena to explore. And in the case of superconductors, the two superconductors, these are anisotropic 3D metals with the multiband superconducting ground state in the weak coupling regime. And these are rare cases of type 1 superconductivity in ternary intermetallics with defects. And all of these are, we've got, half a dozen open projects, and we welcome anybody who might be interested also in participating. Samples readily available for you. So thank you for the talk, for the listening to the talk.